So now that we've established the relationship between standard cell potential, E0 cell, and free energy, or change in free energy, now let's talk about how to calculate the standard cell potential. And the cell potential of a voltaic cell is apologize for the formatting issues here, the sum of the cell potentials of the oxidation and reduction half reactions. And E0 cell are tabulated on the conversion equation sheet in the text with some below. And you'll see I've got a version of this table that is also in the homework assignment. And the homework assignment has all of the cell potentials that you need. Should we need more, I will add and subtract them to that list. Or tell you that you need to go to the conversion and equation sheet. And this is what's called a standard reduction potential table. And standard reduction potential, you'll also see me refer to it as an SRP table. That means that all of these are written as reductions. And we know that when we're going to be putting together a voltaic cell, that something will be oxidized and something will be reduced. When you take a reaction, and let's just take this reaction here for nickel, and its reduction potential is minus 0.23. When we turn that around and write it as an oxidation half reaction, we will take and switch or flip the reactants and products. And the standard cell potential changes sign. So that would now be positive 0.23 volts. Okay? And there's actually a couple ways to do standard cell potentials. This is the way I do it. When I write an oxidation half reaction, I change the sign. I'm happy with however you do it. Just make sure that you document your approach and that you can get the right answer. All right, so on the next page, let's go ahead and take some of these reactions and build a cell. We're going to build an oxidation. So here's an example. Our oxidation half reaction is going to be lead solid going to lead 2 ions plus 2 electrons. And it says for lead that it's minus 0.13 as a reduction. So I am specifically going to call this out as an oxidation, and I'm going to change its sign to positive 0.13. I should have put units on that. That's volts. Good. Okay, and just picking some choices here. So let's go ahead and pick this one here for gold 3 plus 3 electrons. That is written as a reduction, and when it's written as a reduction, you keep the sign exactly how it is. That is positive 1.50 volts. And what we're going to do to get our cell potential is we're going to add these up with a couple key things. One of them is, things to keep in mind here. First, the number of electrons must exactly cancel. And we saw this in a previous video when we balanced redox reactions. We said that you can have electrons, and of course you need them in half reactions for oxidation and reduction, but they will never appear in the overall process. A number of electrons must exactly cancel. And here's where things get different than what we've done before. in order to do that, I'm going to have to multiply this top reaction times 3 to get 6 electrons, and the bottom half reaction times 2, but you do not multiply the potentials. And that's because if we think about what we were doing, the N takes care of that part for us. So the cell potential does not depend on the number of electrons in the reaction, overall reaction, or half reaction. So we account for that later. So, and the cell potential is the potential or height between the two positions. We'll add the N in later. So my note number 2 is, while you must cancel the electrons and you must multiply, so multiply reactions, or half reactions, do not multiply cell potentials. I know, you think we just keep it all straight, so we did the same thing to all of them, but unfortunately that's not the case. So, and incidentally, a third note is that if we were using that free energy equation, N would equal 6 for this, because we'd be canceling out 6 electrons. So 6 electrons canceled out. All right, so we will be canceling our electrons, so I'll just show that here. Our overall reaction will be 3 lead solid plus 2 gold 3 goes to 3 lead 2 plus 2 gold solid. And the way I do it, so remember I switched the sign when I changed this to an oxidation. So I straight add these. I get 1.63 volts. That is my overall cell potential. As the electron moves, not only we're looking at the potential of it being taken away from the zinc, whoop, get up there, getting taken away from the zinc, but we're looking at it being, well, sorry, in this one, we're looking at the potential of it being taken away from the lead and the potential of it being added to the gold, because both of those are parts of that quote-unquote height difference. Let's see. Yeah. So that's our first cell potential. Now, some notes. So, one, that SRP table typically lists half reactions or lists reductions from most positive to most negative. And so, and now I'll actually get the one you'll have on your exams. So it looks right here. You can see I've listed mine from most positive to most negative. And let's see. I think this is on there. Yes. You can see approximately in the middle is this reaction with 2 H pluses plus 2 electrons goes to H2 gas, listed with a standard reduction potential of 0 volts. Let's talk for a minute about that. So that's 2 H plus 2 electrons goes to H2 gas. So this is a reduction potential, and it is 0 volts. Just says 0 on mine, but let's do 0.00. That means if we flip this, the potential for the oxidation half reaction is also the same. And again, I'm happy to talk more about this in office hours or in class, but this is a definition. Meaning, or that allows us to look at the standard cell potentials of ions in solution. And so, because there's no other way to get the ions, and when we use a voltmeter, or when we measure a potential, it's unclear how you do that for ions necessarily. And so, actually, let me think through this for a minute. So, actually, I apologize. I'm going to take that back. This is still a definition, but this definition allows us to establish the grounds, one of the grounds, because there are no absolute cell potentials, just like there are no absolute delta G values. And so this definition allows us to scale the heights of all the other cliffs. So this is a definition, a reference point. Because there are no absolute values of cell potential. Because cell potential is like a height. So whenever you use a voltmeter, you are going, or you're measuring voltage, or you're comparing voltages for different half reactions, you are comparing changes in potential. So there are no absolute values in cell potential, only changes. And we've seen this before when we talk about delta HF values being 0 for certain, the lowest energy version of the element. So that is also true for free energy, delta GF values, only changes. And so you need one reference point, and this is it. Good. And one hint on some of the homework questions and in general, if I give you a picture of either a voltaic cell, which we've talked about, or a electrolytic cell, which is coming up. So we're always looking for the most positive. Or least negative cell potential with the given materials. Okay, so just keep that in the back of your mind as we work some of these problems.